Now, today, as I told you guys earlier, we will switch into deeper and deeper into the network layer. We start from the application. Here's what we want to do. Here's how we will communicate. Here's how socket programming works. Here's how the low-level I/O work. And we kind of left like, hey, there's this thing that's called TCP. And that's also the internet protocol, the IP, and how they would connect. And if you do it in a certain way, it will magically do everything for you. Today, we will dive deeper and now talk about how do we actually deliver the data from one place to another, right? And today, we will do a lot of analogy that compared to a snail mail. Anyone know what's a snail mail? Okay, physical mail. Somehow we joke because it's so slow, we call it snail mail. That's a physical mail, right? What's the purpose of a mail? Communication. You send the data over, right? You have the envelope, and inside them is the text. Same logic, right? And that design trade-off depending on how you run the courier service, right? It can be fast, it can be slow, it can be inefficient, like the government entity run mailing service, right? So they will also compare to that because the way it works, conceptually, the goal is the same. We want to send the data over. Now, layering, which is what we do so far, allows the functional abstraction between each layer. If you think about it, right, when you develop an application, you don't want to worry about how do I slice up my data and send it over to TCP, right? Worst come to worst, I just want to worry about socket programming, write everything in a file descriptor, and I'm done. Yay, that's painful enough, right? Not sure, I think you should agree by now that that's painful enough, all right? And you would let the rest of the system handle this magic. Now, if you go down this layer, right, the interface defines the interaction. Basically, it defines these are what you need to do in order to use my service, right? And you go down from like application to application channel, which is connecting through the socket programming. Then on a more physical side of things, you have one host, you have another host, they want to talk to each other. On a software side, these are two applications, but they are running on the physical machine. And in reality, the physical machine has to send the data, right? So that's a host-to-host connectivity. And the way they send it is they send this thing called packets. Anyone heard about this word before? Think of it as your physical mail. That's the packet, right? What should be on them? We'll talk a little bit more, we'll explore a little bit more, but think about that. Like what should be on your envelope and what should be inside your envelope? Then you have the hardware. In reality, in a mail system, right, is a road, is a street, is a highway that connects different addresses, right? In a network, these are links, right? So to encapsulate this, like you have two processes that want to talk to each other. You can, from the application side, you just do get and then the address, get index.html, and hopefully process will respond with the content of the website. So you send the get command, right? Now, the app-to-app channel would have to give the connection ID to connect to the correct port, correct protocol, right? Then the host-to-host connectivity now have to determine where am I, like the physical address, and where's the physical address of the host. Then the link hardware are just hardware that make the actual connection, right? So what are some sample of the physical connection between your machine right now? Yeah, what are you connected to? Wi-Fi, right? These are physical connection. I mean, it's through the air, right? Data are actually encoded with the message through the protocol, through physics that we learn to map. Actually, there's a lot of maps going them on how to encode this thing in the air and send the signal over. But that's how you physically connect two machines together. What are some other examples of that? What do we call network cable? The Ethernet, right? That's another way to like link two hardware together. So you also have the end host, right? Versus the router. What's a router? It's like a hardware that sits in the middle between two hosts, like audio host and the ISP. Basically sit in the middle and perform routing. All right. So the router also handle IP. It handle internet protocol. In that case, it means that if I have the TCP that talk to each other, under TCP is Internet Protocol, the Internet Protocol packet, kind of virtually, I guess, the data inside them can be sent over to the router. Router knows about the IP information, then it forwards to the next router, eventually arriving at the host. And then the physical connection is done through the Ethernet interface, like your Wi-Fi and your Ethernet cable, right? This is done just to make sure we can send HTTP message. All right. But if we have this established, you develop the application, you don't have to worry about the lower layer. Why do we learn these things then? Why do we need to learn the lower layer? You need to understand how it works. As a computer scientist, that's your job. Because eventually some of you might be implementing these things. Okay. All right. So the first like big topic I will cover after about now is the network link and the local area network. Anyone never seen this word before? LAN. You all seen it before, right? Can someone give me some quick description of LAN? Great job. Yeah. Gaming room which physically connects the machine together, right? So here's the basic building block. Let's abstract away a bunch of things. There's no router, there's no machine, there's no CPU, there's no host, there's just a node. Another node, and I make the link that connect them. All right. This simplifies the design. Everything is a node and they connect through a link. Okay. Now with this, right? There is the super low level question, the electrical question. How do I connect them, right? What's the voltage? Because I mean, when you make a connection, everything you send is electrical signal or optical signal, all right? These days you also have optical signal. So if it's electrical signal, how do I operate it? It's not just voltage, actually, it's more than that. How do you encrypt the data inside this electrical signal? If it's optical question, what frequency range that you want to embed the data over from one place to another? Anyone familiar with like an FM and AM radio? How does it work? So the acronym like FM, for example, stands for frequency modulation. Information from one station that connects to another is encoded in certain frequency range. That's why when you tune the radio, you have to tune to certain frequency range, which if you do a lot of math, which in anyone also know this thing called Fourier transform? They use that. That's one of the most impactful. If someone said that pure math never make an actual impact, that thing probably make trillions of dollars already. That theory, because it's used in communication everywhere. So we can use that to encode the data in certain frequency. Now that you tune to the certain frequency range, you can now extract the data. optical network kind of work the same way. So that's a physical implementation, right? Now you also have wired versus wireless, right? Because the way wireless work is different. It's not optical anymore. It's not like you have the fiber optic cable connecting two ends and send the lights through them, right? Which, by the way, is really fast. Like you fiber optic is light, so you are actually sending the data with the speed of light, right? But with the wireless signal, right, it's a different entity. How do you, again, not electrical question, mathematical question, how do you encode the data over? And then physics question, how do you send the signal? Then the link layer issue, when to talk, but at the end of the day, it's two nodes talking to each other, right? It's like when I talk to you, what's the medium? Air. How do you hear my voice? Vibration, right? That's it. Now, with the air, you can talk, I can talk, and we can all talk at the same time, right? So design issue again, do you want to have the link layer that allow both sides to talk at the same time? Or one side talk and listen to the other, and then the other side respond. And what should be the low level format of your information? Okay. So the next thing is what we call scalability. Anyone seen this word before? Scalability. How big can you make it effective, but still run effectively, right? For example, if I can build a back-end system that can handle n terabyte per second of bandwidth, and then the company get bigger. Now I have to handle 5n, 5 times bigger. Can I use the same system, but do replicate this system, make it bigger? And it's still like I pay 5x the money and then I get 5x performance. That's a pretty good scaling. If I pay 5x the money, I get 2x performance. It's not as good. Some system, I pay 5x the money, I have way more machine. You get a half of your performance. Why? Communication. You have to like have the machine sync, and that can be the overhead as well, right? So here, you connect multiple nodes together, right? And one way you can do it, you have one wire that connects to every machine. What's the problem here? Flow. Why? Well, I mean, think about it this way, right? Yeah. Yes, and yes. So everyone, whatever everyone says, yes. Basically, a wire is electrical circuit, if you think about it, right? And most of the time you would represent your data with some voltage value, right? 1 or 0. Now you have one wire. So at any given point in time, how much data can I send over? 1. Which means I have node A want to talk to node B. It means, yeah, they can talk and they took over the wire, right? If node A wants to talk to node B and then node C wants to talk to node D, they have to wait. Only one of them can use it. Sometimes we call this a bus. Why? How does the bus work? If I want to connect to two places, right? They will only run between the two places. Then you have to reroute, not rerouting the bus per se, but you have to run like differently, right? Yes. No, it's actually the sometimes we call a bus when we want to basically make this like one single resource that connects multiple source and destination. Yeah. Now another alternative, everyone got a wired connection from like let's say I have n node, right? I connect to all my neighbor. I connect to every single other node. Is that a high performance system? Is that costly? Okay. So sometimes we call this thing crossbar. which is or if you will, we call it all-to-all connection. Literally all-to-all means that every single one saw each other. But these are, well, for a really, really high traffic area, right? I mean, it could be really nice. If you don't have a lot of nodes, for example, like 10 nodes, maybe that's okay. How many nodes are there in the internet? Even just devices in your home, at your home right now. Everyone has their own smartphone, right? So that's one devices. You maybe have like a smart app that connects to like all this light bulb, the door. If you fancy like thermostat to control the air conditioner, I don't think we have it here actually. Do we? Do we have the smart thermostat that control AC
in Thailand.
in Thailand? Okay.
If you spend money,
If you're rich, I guess you can buy them. Okay. Yeah. Yeah, but that's many devices connected to the internet, right? Maybe all-to-all connection might not make sense because how often do everyone talk to every other all the time? Not often, right? I mean, you think about this. Your phone is likely just connected to the router and that's all. Everyone connects to the router, but they don't talk among each other, right? Most of the connection is done that way. So you can design, somehow we call this topology. Topology dictates how we put the links between the nodes, okay? And it has to do with scalability. It has to do with cost. Now here are some metrics of interest. Latency, you've seen this before. It's the speed. Think of it as the speed. If I do some action, how long do I have to wait for that action? Capacity means somehow we also use the word bandwidth. If I want to push things through the network, what are the bits per second that we can push them? That's also this keyword I would add on here called bisection bandwidth. Bisection bandwidth is if I have a network and I have a knife, I cut the network in half in a way that like I totally isolate the two sides. What's the bandwidth of all my links that connect the two halves together? Because that tells you potentially how much you can put through from one side to another. So that's bisection bandwidth. Jitter is, well, you use network before, you play online games before. Sometimes it runs well, sometimes it doesn't run well. And when it doesn't run well, you basically curse your friends. All right, so yeah, that's a nice thing to do in online game. But jitter is basically that, the variation in the latency, because sometimes it's not like everything, not in a network. There's so many things involved that sometimes things are slow, sometimes things are fast. Reliability, can you drop a packet? If you send a packet over to get dropped, how do you detect that? And is it okay to drop them? Reordering, if I send A before B, should it also keep that order or it doesn't matter? So these are the metrics of interest. For example, you want to reduce jitter. You don't want to make the latency variation really high. But if you try to reduce the jitter, but that comes at the cost of, then I will just make sure everything is slow. That's also a bad thing, right? So these are things that you want to set as a goal, and they have trade-off. So you want to pick the right trade-off for your application. Another things I need to share, the keyword is multiplexing. Multiplexing is, well, network resources are shared. And I have multiple parties that want to use the resource. Who get to use when? Sometimes party A get to use it, sometimes party B get to use it. It's being multiplexed. All right. Now, what would be the mechanism that would allow you to share the resource and how to multiplex this resource? And in the old days, right? Definitely, I'm too young to see this, but our, like, probably your uncle, right? Your parent generation, Maybe they're too young too, actually, to be honest, like a long time ago. Yeah, when you have to do the plugging, right? That's an operator that in the actual office, when you make a phone call, you call the operator and say, hey, I want to connect to that house, and they'll make the connection. We call this circuit switching. Been used before. It's possible. What's the trade-off? Slow. Uh-huh. Operator can also make mistakes. That's actually a good like you have to program the middle, like to make sure that it's the right connection, right? Depends. You can, well, it doesn't, it's not true actually. You just make the link, no one can listen to whatever is happening. So that's circuit switching. Now, what we can do is called packet switching. All right, I have a source and I have a destination, and I built a packet. These are self-contained information that I want to send to an address. It's like your actual mail. You put everything in your mail, you send it. The whole things go together, right? In reality, the source can also break the packet up and send parts of it at a time, right? But here's the key issue. Or not key issue, but here's the key idea. When I have a packet, each packet can travel to the destination independently, because you, again, compared to actual mail, you send 3 different letters, they can go in whatever way they want, they just arrive at the host, right? They can take different routes. And then the circuit switching switches in the middle, right? That's the operator. Now the switch in the middle is used to figure out how to forward to the next step. So now everything in the middle is just, hey, I have this option to forward. Which one do I pick? That's kind of like the actual letter, right? The postman basically look at all the address you have to go to and then figure out, okay, which route am I gonna drive and deliver all this mail? Okay. Uh, here is one case study that we will talk about is the Ethernet packets. Somehow we call it frames. And you've seen it before in real life, in practical sense, you use it before. Study what's going on. So the Ethernet packet encapsulate the IP datagram. Basically, if you want to send one packet from one place to another, you need what? IP. You need that. Otherwise, you cannot send, right? You need the source and you need the destination. Everything is in the Ethernet frame. That includes things like, where am I going to? Where am I going to? Where am I coming from? What's the data? These are preambles that are specific to the Ethernet frame. The key idea is this is similar to a snail mail. You think about it. What do you have to put on your envelope? To and from, sender, destination, right? That's it. If you have that, and if you have a working system and a working link, the postman can deliver your mail, right? So that's the key idea. The data is in the middle. That's what you want to send over to the destination. Okay. Now for the address, that's each Ethernet adapter has their own unique ID. What do we call this thing? Anyone know? The MAC address. It's unique globally. It's unique globally. Give me a second. If this I already have a lot of like depth. Why asking for more loan? No. Anyway, so with this, you also have the unique address, which is FFFFFFF. We call it broadcast. Broadcast ad name. So yes, everybody will hear that. Okay, so you can also send a broadcast message. The type will indicate the higher layer protocol. Most of the time, these are IP, but it also can be used to support something else if you want to. Basically, if the higher layer needs anything, put it in the type field here, right? So as you can see from this Ethernet frame diagram, you have the IP, you have the TCP header, so it knows like, okay, how do we connect and what's the TCP header, what's the port, what's the socket, all those things. And then you have the application data that you want to send. At the end of the day, once you have the application data, right, these are the HTTP requests, for example, get on whatever, right? These are the header from the application. These are the actual user data, for example, the content of your website. So you see that these are, think of it as like multiple layers of the shell that you like peel off one step after another until it reach the application layer. All right. Now with this Ethernet packet, right? Packet switching in the Ethernet, the switch takes your packet. Now it has to forward to the destination. What are the design issues we have to think about here? Packet loss, right? What else? Think about it this way again, compared to service mail. If you have to run a mailing service, what would be your main concern when you design the whole company? To deliver all the message, hopefully no packet loss, hopefully reliable, hopefully on time, hopefully fast. What route path planning, right? So these are the design issues. All right, now let's focus on how do I forward. Again, these are a bunch of intermediate nodes that you have to forward from one source to the destination. Your task is to figure out where do I go next, okay? So Ethernet frame, again, the Ethernet packet, the way you would forward, right? The idea is actually simple. You keep a big table that has the MAC address and the port. The machine that has the MAC address is a part of the table, and you would have the port of your switch. You have the port of your switch. And for every packet, the switch look at the destination. It looks at the destination. Then you forward the packet on the port. Yes.
My misconception is like the internet switch, the internet frame, the same as network switches.
Oh no, internet frame is that packet that you want to send. Your message. Yeah, your message.
The internet frame forwarding is done by network.
It's done by network switch. Yeah. Network switch handle where to go next. Now, here are some design issues, right? If we keep this table forever, what would be one big glaring issue that you can run into? The size of your table is going to keep growing as we connect to more destinations. So there's a timer that say, hey, this connection has been there for a long time. This is old, kick it out. All right. What is this? Why is this useful? So if you look up and you find your address, you go to the port. If you look up, first of all, you don't find the address, what do? Broadcast and kind of figure out where to go next, right? Now, also, if you look up, find the location where you have to go. Now you go to the port. It's always, this means that you book that port. Basically, that address book the port for the path. This also make the assumption, which basically means that I can forward my packet forward one hop. A hop means I go from one node to another, which means I move one hop, right? And hopefully with this table, I move one hop closer to the destination, which means that everything will arrive. Okay, with me so far? Okay. Now, here is one of the tricks, right? One thing you can do is for every time you connect to the internet for the first time, I will populate the table myself and list every port. And say, okay, that's my address go here, that's my address go here. That's going to be time consuming, and that can be error prone as well. Sometimes link is gone, right? The way Ethernet handles this is using what we call learning bridges. Learning bridges basically suggest that I'm learning something as I go. I make the bridge that connects two sides as I go. Basically, every time I arrive through some source send something to me, my learning bridge will know, hey, I have the connection to that guy. Okay, so you can build the table. You can build the forwarding table based on that information. I mean, you don't have the information how to go forward, but you know how to go back. Which means if you have a traffic from the other side, you know where to go. Which means that if you keep building this table, you have the information on both sides of your ends. So the learning table basically look at where the packet has been. Because that information is known, the packet will have that. I have the source, right? Definitely I know where is my source. And because it arrived at this location, it means that that's a path between the source to me. Yeah, basically I have that. I have a source that comes at my location. I don't know where's the future, right? But I definitely know that if someone wants to go to that location as a source, like if the source was someone else's destination, now you know where to go. Because you can basically make this bridge back here. Yeah. How does that help? Because eventually you get packets from everywhere, which means now you know where to go everywhere else. Yeah. So that's how you can build that table. Mm-hmm. Yeah. Yes, but okay, the trade-off here is, do you want to build that table by hand or use this mechanism? Right? So that's why we have to do this. Because we don't want to populate the list of source and destination by hand for every single switch. All right, now, any questions before we go to the network layer, the IP? All right, so now let's look at the network layer on more of the theoretical side of things, right? What are they? So they are designed to transport packets. These are again, this network layer, think of it as the connection between your addresses, physically, your street, your highway, right? You have the sender and you have the receiver. And the network layer is there in every single internet devices, the host and the router, because you need this to communicate. Now, for the functionality to actually communicate, you need to be able to do two things. You need to know how to forward, how to move packets from the input to the correct output. It's like when you go into the intersection of like you're driving, you have the intersection. You need to know how to turn left. If you want to turn left, you need to know how to turn left. That's how to forward. Then you need to know the route You need to, while you're driving, you need to know, okay, you're turning left next, followed by going straight, followed by turning right. So the forwarding mechanism and the routing mechanism, okay? With this path, you want to turn left, you want to turn right. If you want to go to that destination, how should you drive? What's your path? Okay. Then that's a service model. The service model for the internet is what we call best effort. What does it suggest? try our best. Yes. Why does it kind of make sense for the internet? It's first of all impossible to be 100% correct. It's too costly. There's too many parties involved, right? People who use the internet is literally probably like close to 1 billion people, right? There's no successful datagram for the delivery of something to the destination. I can have a malicious server that just absorb the packet and never do anything, right? The timing and the order of the delivery is also, I'll do my best. There's no guarantee. The bandwidth available, also, I'll do my best. There's no guarantee. Yes. Yeah. So your question is, if I'm sending my data through router through one hop to another, wouldn't that be bad? Because someone can look into my data. Great question. So if you think about the privacy concern, security concern, one thing we can do is most of the time, if not all the time, we will encrypt our data. Now go back to the OS module about privacy and security. Remember one thing. Our encryption mechanism should be good enough that if the router wants to peek into what's going on here, if 100 years, then they might figure out, but yeah, 100 years. So that's the, again, best effort as well. I'll make sure the encryption works and make sure that hopefully if someone wants to see my data, by the time they saw the data, they either die already, like physically die, like 100 years or more, or the data is not useful for them anymore. If you can make the guarantee that the data is not going to be useful for that guy anymore, it doesn't matter, right? That's, for example, why for things like one-time password is quite powerful. If I use it once, yeah, that's it. I don't need a key anymore. Then I will generate the second one. Then I'll generate the third one, but I can only use it once, right? In terms of quality of service, so that's a new name for you, quality of service. What it means is, well, actually, if you look at that word, what would that suggest? Well, internet is a service. I try to access something. I try to send the data through the internet. I try to receive some data, right? Quality of my service will be something like, do I get all the bandwidth? Do I get 1% of the bandwidth and some other guy get 99%? Do I have packet loss? Do I have any guarantee on the timing? No, doesn't exist for the internet. We'll do our best. Hopefully it works for everyone. Okay. So to kind of think about why do we design the internet this way? I think this goes back with my question. Why do we just do best effort, right? This allows the internet to be easily adopted. I'll just do whatever I want to do. If I run a company that connects to the internet and somehow the server on my end is super slow, well, yeah, no one would use your service, right? And that's okay, because there may be other alternative services that's better. Internet provide that possibility. Most real-time application, if you have some provisioning, means that I guarantee that I will get at least this much bandwidth. Anyone heard about this word real-time application before? Okay, good. One unique is not about how fast I have to be, but it's about deadlines. Real-time applications have deadlines. There are two types of deadline, soft deadline and hard deadline. Imagine hard deadline as, let's say you have an autopilot program and it has to make the decision whether it should go that way or that way. The hard deadline is the point of no return. If you don't make the decision by this many seconds, someone will die, someone will get hurt. So that's the hard deadline. Self-driving car. I see some random object. The object detection better be able to make the decision by the time I can brake. Right, so that's the deadline. How about your game? If I want to render one frame on your screen, what's the deadline? Look at the refresh rate. If let's say let's go with the cheap monitor, right? 60 hertz. It means that every 1/60 of a second, I better have another picture I have to render on the screen. That's a soft deadline because will someone die missing that? No. Is that annoying? Yes. Again, real-time application as well. So that's why a lot of interactive application, a lot of like things like video streaming have the real-time deadline. A lot of people might confuse real-time with fast. It's not about fast. It's about just meet the deadline. In fact, if I have a GPU that can render 500 frames per second, are you going to try to render 500 frames or just 144? Right? There's no need to burn the power to render 500 frames because you're not going to use it on your monitor. So the goal in many cases is just hit the, make sure you don't hit the deadline and you don't have to be that fast. Okay? You need some bandwidth to guarantee that, hey, if I have this much bandwidth, I can, for example, detect this object by the time the car can brake, not after. Okay. All right. Then you can also have a replicated application layer. It basically means that I have a replica of the application somewhere else physically. In case something goes down, then I can just connect it here, right? But one thing you might have realized that when Gmail doesn't go down that often, right? Google doesn't go down that often. Facebook doesn't go down that often. It does happen sometimes. How about banking apps in Thailand?
Oh, every time, every day.
Yeah. See? But if you know system, I mean, you can make a decision too. I mean, to be honest, they might be making some economic decision and say, hey, this is cost effective. Why do you have to pay that much, right? I just let the customer wait to buy like whatever things you want to buy until the server is back up. Or if you or me and many of you too, you just ended up having too many bank accounts. If one app died, I use another. But it is hard to argue with the success of the best effort service model because it's simple and it allows the user to do whatever they want. All right, network layer, the internet. Here's the key function. So I have a network layer. It connects the transport layer, which is a TCP or UDP, and the link layer, which is your actual cable that connects things, right? Your network layer has the path selection algorithm, which means that now if I have this guy, I know where to go next, okay? Then you have the IP protocol, which has the datagram format for trying to figure out where do I go, okay? Where do I go? And then that's the ICMP protocol, which report error and perform any signaling. The good thing about ICMP protocol is it better than just have no signal? If I have no signal, something goes wrong, I have no idea to tell. This allows me to tell him something might be going on with the network layer to figure out what to do with it. The IP packets, you've seen something like this before, right? But here is in the network layer, here's what the IP packet would have to look like. Just go with this diagram basically. Version number, the header length in bytes, which will tell you how big is my header because you have like optional field for the header. Total datagram length in bytes. We can use that to kind of confirm that here is the datagram, not longer and not shorter. To double check that that's the correct thing. The header, then you have the identifier, the flags, any offset, fragmentation, and reassembly means that if somehow my network doesn't send the packet as a whole, what does it mean? I have an IP packet, right? And it's as if your mailman slice your packet in half or in 4 pieces and deliver one piece at a time. Why do we do this? Actually, this can be better for performance. In many cases, you might want to do this. Then that information is there to figure out how do I put it back into a packet when I am at the destination. ETL, remaining max hop, basically means that if I want to get to the destination, I have to go at least not more than this. It's remaining max hop, basically. Then the upper layer bits tell you is a TCP or UDP. And then in the last part, header checksum, basically just to make sure every bit you see is correct. So you put in the checksum. Then you have the source IP address, destination IP address. How big is your IP address? Can someone tell me? 4 byte IP address, like something dot something dot something dot something. Each thing is 0 to 255, so it's 4 bytes for the IP address, so it's 4 bytes for the source, 4 bytes for the destination. Then you can have any optional field afterward. These are most of the time for extra information like timestamp of the packet so that you can maybe rearrange the packet inside the network. Or the record of the route taken, maybe that's to establish the path by the router so it can smartly adapt to like, hey, maybe go there. Then you have the payload. Payload means that's your data, you understand? Now you have the two things, right? Addressing and route finding. Route finding is I look at the forwarding table and figure out where do I go. Right now that's the issue. One easy way to fix this is use a trick that we call subnet. Anyone seen this word before? Subnet. How about subnet mask? Basically, the idea of the subnet is, as the name suggests, is a subnetwork. It's basically the list of devices that I can get from X to Y, without passing through the intervening router. It's a sub part of the network that's kind of connected already. It's like the highlighted portion here, right? The highlighted portion here, you have the router in the middle. The rest are just switches. So you can basically talk among the subnet. The IP address have the way to embed the subnet. What it means is some part of your IP address also tell the subnet. Some part of your IP address are just to tell where is the destination or where is the host. Okay, so how to represent this? We can use the technique called CIDR or classless interdomain routing. I have any length for the subnet port that you can configure. So basically, if you have to configure your router, you can configure your subnet mask, which tells you these bits will be a part of the same subnet. These bits will not be a part of the same subnet. And the way you represent that is you have the IP address followed by number of bits. These are basically number of bits I will use for the subnet. In that case, 23 means I'll take the 23 top bits. Those are my subnet. anything that fall in that range and are the same number, they are a part of the same subnet. Okay. Now with that, right, things are simple or simpler, I guess, to figure out if I have a bunch of destination, right? If actually now, if I'm trying to route and forward the packet, it's good if I know they're the same subnet. So I can look at the connection, and then I have this table that say if my destination fall into this subnet, I go to the link interface 0. If it's this subnet, I go to link interface 1. If I have this subnet, go to link interface 2. The way I'll do that, they have an incoming packet. Again, they'll have the destination. The way I detect what subnet do I forward to is I just match and pick the longest prefix. Whatever is the longest, I go there. For example, the first example is that it maps to this bit. So you go to link 0. This next packet also, the thing is this next packet maps to here and also here. Again, it maps here and the same packet also maps here. In that case, you go to link interface 1 because they are longer. So you go to link interface 1. All right, now that's about subnet. The next thing is whenever you connect the device to, for example, the Wi-Fi router for the first time, what do they do? Oh, anytime actually. They assign me the IP. You might see it's also IP conflict sometimes, right? But most of the time you will be automatically assigned some IP. That becomes your address. So the router knows how to send the packet over. So now the question is how do I get one, right? There are actually two questions. How does the host get the IP within the network? And how does the network that I'm in right now, like Mahidol University network, get the IP for itself, right? So the host can get the IP by two methods. The first one is I just assign the IP manually. It's called hard-coded by system admin, right? Why are these useful? If you have a really, like, if you have a server in a network and you want to make sure whenever this server is connected, you can get there with this IP, assign them, right? Or you can do plug and play using the DHCP, Dynamic Host Configuration Protocol. Basically, the router picks the IP for you, right? And the way it works is you have the DHCP server, right? Because in a network, you should have just one of the guy who just assign the IP for everyone else, right? So in that case, the new clients that just connect and plug into the network will ask the server, hey, DHCP server, is there a DHCP server in this network? If the reply is yes, in that case, the DHCP server will reply, say, hey, I am the DHCP server. The client then would ask, okay, I'm a new guy, I want an IP address. Then the DHCP server pick and address that's not assigned yet, give it back to the client. Two hops. Not two hops, two round trip. Are you there? I need an address. Okay. Now the next thing is I have a network like Mahidol University. How does Mahidol University get the IP so that everyone else in the world can get here? All right. That's allocated by the ISP, Internet Service Provider. They'll give you some address space, and each organization can basically allocate the space, right, to the network. Yes. So as far as I'm aware, this is probably can be done manually. I'm not sure if there's like automated mechanism to that because whenever you sign up for a new network and register to ISP, right? There's likely a table that keeps like here's the existing ISP and it's not used one and here's what I assigned. I guess if you want to do, you can automate that. I don't have information on that. Let me look it up for you. So can you remind me or send me an email? I'll definitely reply back to you. Now you have the way to establish everyone's address. The next question is, how do I forward? Basically, how do I forward data? How do I know where to go, right? For an organization, or somehow we call this autonomous systems, there are two sources of information. It will also, first, it will get the external route advertisement. External route advertisement basically has to do with, here is the route from external source that are available and you might want to use if you want to get to the destination. So that's the external route in the internet. Why is this useful? It's kind of like a predetermined route given to each organization. So if I want to from here connect to Google, I know where to go. All right. And it's advertisement because it's basically a declaration that this thing might exist. If you want to use it, try it out. All right. And it's likely that it should work. You can read more info about this thing through the keyword BGP messages. Then inside the local network, most of the time, I mean, the simplest thing you can do is shortest path, right? Some kind of shortest path algorithm. Yeah. You can also do adaptive routing, which means that if that path is super congested, I might use another alternative route as well. Now, that's also the NAT. You might have seen this also, NAT before. The acronym stands for Network Address Translation. Now, with the acronym meaning, you probably can figure out, okay, that's something that has to do with translating the network address. Why? I mean, your device in the local network, like your laptop, your mobile phone, right? From the outside world, it's the same IP, connected from Mahidol University, because it's the same network, right? Anything that leaves the local network will be assigned the same IP. But here's the difference. You have different source port numbers, because you establish that physical connection. And inside the network, now if you're in Mahidol University and you ping another device in the same network, you get the local IP. So outside you see the global IP, inside you see the local IP. Anything in the local network will have the 32-bit address private IP that can only be used locally. This kind of separate out the like the network with the devices. This also allows the ISP, for example, like AIS and True and other ISP to actually say, hey, every device in this network, this IP, simplify a bunch of things because they are physically connected anyway. If I send it to this IP, there's like same location. Anything happening inside the local network, like I have new devices connected, my ISP doesn't have to be aware of that. Doesn't matter. What happened inside the local network is not seen by the ISP, simplifying things. Anything that I want to do with the ISP can also change because it's just a router that serves like interface with the ISP, right? So that's okay too. Things that inside the local network also not visible to the outside world. So you have some security guarantee as well. Okay. So in here, NAT router must do all these things. First of all, have to figure out the outgoing datagram for every packet coming from the local network that want to go outside, you now need to figure out the new port number and the NAT IP address so that it actually can go to the destination outside. So that's done silently inside the NAT router. Also, it has to have the table for every source IP and the translation pair. So it knows that, okay, this connection pair go from this source to this NAT IP address, so that you can establish the connection with the device in the local network to the outside world. Then you also have to do the incoming datagram from anything from the outside world, because anything from the outside world, the destination is going to be the network IP, not my local IP, right? Now you have to replace that with the local IP address with the correct port number in the NAT table. So it basically has this translation table that provides the mapping from the outside world to the inside. And here is how you do it. Yes. Yeah, basically it's a giant table. There's a WAN side, wide area network, the outside world, and the LAN side, which is the internal network, the local network, right? And simplifying thing, I have the IP port. That's it. I can look up the table, I know where to go. Because in the case like 10.0.0.1 port 3345 is now connected to that IP port 5001. Now my NAT router knows, okay, if there's a connection from 10.0.0.1 to this address, it knows where to go. Yes.
Where is this guy?
Inside the router.
Wait, so I thought that we had only one address for one area.
Yes, but it has multiple ports. So you can keep multiple connections. Yeah, so it would establish that pair.
So the ISP.
Because if you think about, remember the networking application lecture, right? You have to open, like ask for the connection, then open the connection. That time you assign the port. Yeah. All right, so now this is a little bit extra about that because it's been controversial in a sense that the router should only process up to layer 3. So networking has multiple layers. You can look it up, like what does layer 3 mean. That also limited IP address. Well, right now we don't need it yet, but that's also IPv6, right? Then, in many cases, your computer would like to have the end-to-end and like secure connection argument where your machine, if you go to Google, it should be kind of like direct connection. But you have this router, which is the network NAT router sit in the middle listening to all these things, right? So it does have this port manipulation that can happen in network layer device, right? And what if the client want to connect to the server behind the NAT? So it's not really, it's like it's a design trade-off in a sense, right? You have this simple table that makes the connection, but you also sacrifice some of these things. But it's gonna be here to stay. It's extensively used in home and it's like everywhere actually. Okay. And here's the ICMP protocol, the Internet Control Message Protocol. This is used by host and the router to communicate at a network level. This actually is like when you want to talk to the router and see what's going on, you can use the ICMP as a protocol. This is used for error reporting, to figuring out things like I can have the code 0, type 0 for echo, just reply, ping me back. Type 3, code 2 is, for example, the destination protocol is not reachable. You can have like destination port not reachable, destination network unknown. So these would allow you to what? As a programmer, help debugging This is like you see some status code. It's like 404 versus 200. You know what's going on. Okay. ICMP message will have the type, which is the first column, plus the code, which is the second column, and the first 8 bytes of the IP datagram that caused the error. So you know who caused the error and what's the error. What goes on from there, you figure it out, but the router connects to you and say, hey, this guy caused an error and here's what happened. You can also kind of do this, like, let's say I have a source that set up the UDP segment to the destination, right? The datagram will, like the datagram is the end set, and the end set is defined by, for the first set has the ETL of 1, maximum hop. ETL is the maximum hop of 1. Second set has 2, third set has 3, so n set would have n maximum hop. If I have the n set arriving at the n router, the router discards the datagram and send the source IP message, so type 11 code 0. So this is what we do by trace route. I want to go at maximum these number of hops to the n router. Can I get there? And we stop when my trace route mechanism arrive at the destination. Good. That is basically what minimum path I can get to the destination. I start from 1 hop, 2 hop, 3 hop, 4 hops, 5 hops. If it's not there, I keep doing. Then at the m hop, now that I have the destination, I say, hey, I know where it is. And the source stop. So the second criteria is if ICMP say, hey, the port is not reachable, I can't get there. I also stop doing it as well. And the reason why we call it trace route is to trace the route I can get to the destination. Simplifying the whole mechanism is like, everyone know breadth first search, right? What is breadth first search? Go one level at a time and see if I get to the destination. Same thing. I try 1 hop, I try 2 hop, I try 3 hop, try 4 hop. Listen to the message. If I got there, good. If I have no path to destination, good. I stop. Well, not good, but I stop. Right. Now, let's do a quick break before we actually transition to the actual live session. It's supposed to be a pre-lecture. Yay. And as usual, how many people actually listen to pre-lecture? Oh, you did. Thank you. So now we have a transition to the live session. We forget about recap because we just talked about that, right? Now we will talk about. I will talk about real world case study on a server that actually died, so we can't do that, but I'll kind of go through that. Okay, so we'll resume after maybe let's do 11:35, 7-8 minutes. Okay, so sorry, forgot to unmute. Basically, the key is internet and the design are shifting. Back in the day, router switches just acts like a connection between your computer and the server between the server and the server, and between a computer and a computer. Most computation are done inside at the edge, basically, at your computer, at your device, at your server. Now, the model changed quite a lot these days. There are proposals that maybe we can do a lot more things in the network because the hardware is more fancy. The network actually, these days are also programmable. It can actually program. You can put some programs in there to perform some tasks. There are actually quite a lot of research that go into now. If we can do that, what are the fancy things we can do? You can program the network. Somehow we call this like things like software-defined network. Software-defined network is not defined just by the hardware implementation, but we can program them and rearrange, reroute, and apply certain policies. You can also do programmable network interface where data coming in, I want to do something with the data before I send it over to the host because I want to be more efficient. I want better performance, right? So now things are changing, and it's actively changing right now. The internet and your network that you will see in the next 10 years likely different from what you've seen so far in the last 20 years. And it should be better, to be honest, should be better. Now, the last thing I want to talk about today is a hands-on demo because your project too, you are likely to be stuck with debugging, right? And one of the problems is you write your code, you don't know if you send things correctly or not. Or if you got the message, did you got the right message or not? To simplify things, why don't we do some debugging in Python? What I mean is when you're about to test your C code, try to replicate what you want to do in Python, send that to the server, and see if you get the same reply, because Python has the API for that already, and it's conveniently done. So here is the demo. So if you go to directory number 13 in the GitHub, there are two things that you can see here. hcrequest.py and socketrequest.py. So if you look at HC request, right, this is basically, well, the first thing you see is like you have import http.client, and we make connection. See how connections make here. Con equal http.client, which is what we import already, right? Then we put in the host name. We put in the host name, which is pretty convenient. Just look at the host name here, port 80. There's no get IP, get name, whatever. Put in the host name. Now I can set the debug level to be 1. All right. And I can assign headers as, like, for example, here, accept, explain, blah, whatever header you want to put in. Then you can send the request by doing the connection.request. With the request type, for example, here, get at the root in this case, I guess, basically, if you go to cs.muic.macedon.ac.ch, you get basically that location, the index.html, with the header. And then you just do response equal con.get response. Afterward, you can print the response. All right, this allows you to test the packet and see what response do you get back. That means also if you want to send the same request over using your C or C++ code, do you see the same thing? If you don't see the same thing, something is wrong, but you can now test it here. All right, yes.ปิดไฟ Mike? Where? Is it still off? Huh. It's on here. Hello. Yes. Can someone hear me? Okay, you can hear. Okay, awesome. Yeah, basically now the script allows you to make the connection easily using Python API. Then you can set a header that you want, assign them using the con.request. Con is just your connection. You can use whatever name you want. Then put in the type of request like get or post or whatever. Then you put in headers equal header, that becomes the header part. And just say, hey, I'm gonna get response, right? Let's actually try to run it. Now, Python HT request, right? So here, this is what you got. I send a request over with the header, see? Server reply back. What's the server's message? (301), right? Look down there. 301 move permanently. Why is that the case? Well, for some reason, if you go to cs.muic.mahidol.ac.th, it's not there. If you go there right now, get forward to muic.mahidol.ac.th. I don't know what's going on, to be honest, but yeah. So I guess we can modify that. SC. Wait, what's the muic.mahidol.ac.th? All right, let's try that. Now you say we got found. Okay, for the HC, just the header. Now if you go to socket request.py, this basically establishes the socket. Which allow you to send things to the socket. S is the object for your socket, and you can connect to, like in this case, you see it again, move permanently as well. So let's try that. Socket here. Then wait some time. Now you got HTTP 1.1, the version, move permanently again, right? So we can then modify the address to just muic.mahidol.ac.th and run. Oops. It's found. Here's a location, blah, 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 and then close the connection. All right, so any questions so far? So you can use this script, change to the address, whatever address that you want, change the message in whatever you want. The demo provides, for example, the socket will you can see here that it has the message, the sample of like how you send the message. All right, again, don't forget the /r/n for every line. All right. So actually, it's 11:50, so I need to prep for the skill lecture. But feel free to actually try for now, because and from what I've heard so far, many of you actually start project 2. Recommendation: do it as early as possible. Every single semester, this is the project that gives you the most problem. Not project 3, not project 1. Project 3, to be honest, even with the new one, is pretty straightforward. It's really straightforward if you know what you have to do. Just trust me. I'll ask this question later when you guys finish. Yeah.
It's easy.
And so that's it. That's a wrap for the class today. If you have any exam today, good luck on the exam. If you have any other exam this week, good luck.